This is video help on homework number 5, and this is problem 11 in-class assignment. The first thing you need to do is figure out what lambda is, and that is the ecliptic longitude or planetary longitude for Jupiter on this date. So what I've done is I've found the nearest date in Appendix 11, and notice it says right here planetary longitudes. That's the same thing as ecliptic longitude. So there I've found the lambda for Jupiter on that date. Then it says assume that Jupiter is on the ecliptic. Now beta is the ecliptic latitude. So looking at a star chart, the lambda is the value along the ecliptic, beta is above or below the ecliptic. So that's the ecliptic latitude. And if you assume that a planet is on the ecliptic, then the beta is simply 0. So that is an approximation. Planets are not exactly following the ecliptic, but this is close enough for our first approximation. As you learned from page 1 of the homework, the obliquity is the inclination of the Earth's axis with respect to its orbital plane. So we're going to use 23.5 degrees as an estimate for epsilon. Then to find alpha and delta for Jupiter, I'm going to use the equations from section 27 of this textbook, which is the practical astronomy with your calculator. The equations look like this: inverse tangent and inverse sine for the alpha and delta. And here we have the ecliptic latitude, the obliquity, the ecliptic longitude, obliquity, latitude, so forth. And then you're also going to find out what the local sidereal time is using the star charts. To do that, using that date and time, you'll use this equation here to figure out what the hour angle is. Make sure you record that in degrees. And then you use that number down here when you're calculating the altitude, and also you'll need the your latitude from a previous problem in this calculation to find the altitude and azimuth. Now these two will always be correct when you take the inverse sine. There'll be no adjustments that you need to make as far as what quadrant they belong to. That's because delta, which is declination, and A, which is altitude, is always between -90 and 90 degrees. So there's no quadrant adjustment needed there. However, these require some kind of quadrant adjustment. The alpha and the azimuth might require some adjustments. So to take a closer look at that, if you rewrite that alpha equation such that it's a y over x, going back over here, this all in the numerator is y, the denominator is x. There's the inverse tangent. So again, if you write it like this, where it's y over x, it gives you some rules about what adjustments might need to be made. So if you want to look at this section, this is page 53, and then you can refer to figure 29, as this summarizes it really well. For example, if y is negative and x is positive, you'll want to make sure that the alpha that you get from the inverse tangent is between 270 and 360 degrees. That might mean that you need to add 180. It might mean that you need to add 360. But you need to kind of force it to be between 270 and then 360 degrees. Now azimuth will come out in degrees here, but note that after you get an answer in degrees for alpha, that you will have to convert that to hours. So this is a complicated problem. Hopefully some of this video will help you go through that complex process, and let me know if I can help further with these kinds of questions.